Atom structure and the Standard Model. Atom is the smallest particle of an element that retains its identity in a chemical reaction. There are three subatomic particles: protons, neutrons, and electrons. Protons and neutrons are located in the center of the atom, called the nucleus. Protons, in red, have a charge of +1, and neutrons, in blue, have no charge. Electrons are the smallest subatomic particles and move constantly around the nucleus. Electrons, in gray, have a charge of -1. Quarks. According to the Standard Model, there are the building blocks which build up matter. They are seen as the elementary particles, also called fundamental particles. There are 6 flavors of quarks: up-down, charm-strange, top-bottom. Quarks are bound together to each other by the strongest force in the universe, called simply the strong force. This enormous force binds them so tightly that one quark cannot exist by itself. Quarks make up protons and neutrons. Up and down quarks join together to make protons and neutrons, and they are glued by gluons. In the picture, we can see protons are made with 2 up quarks and 1 down quark, whereas the neutron is made with 2 down quarks and 1 up quark, joined together by the gluons. The gluon can be considered to be the fundamental exchange particle, underlying the strong interaction between protons and neutrons in a nucleus. The gluons are in fact considered to be bicolored, carry a unit of color and a unit of anticolor. Leptons. According to the Standard Model, they are, as quarks, the building blocks which build up matter. They are called fundamental particles. There are 6 flavors of leptons: electron, muon, and tau, and their neutrinos: electron neutrino, muon neutrino, and tau neutrino. Leptons have various intrinsic properties, including electric charge, spin, and mass. Unlike quarks, however, leptons are not subjected to the strong interaction, but they are subjected to other 3 fundamental interactions: weak, gravitation, and electromagnetism, excluding neutrinos, which are electrically neutral. Leptons make up electrons. According to the Standard Model, electrons are actually one of the leptons which has a -1 charge and a very small mass. All other leptons can decay or transform into electron leptons or electron neutrinos, which are more stable. In the picture, we can see 3 generations, and the 3rd generation is a tau or tau neutrino, that is the biggest one. These can decay into a muon or a muon neutrino, that is the 2nd generation, or back again, it can continue decaying into the 1st generation, that it will be the electron or electron neutrino. This is a summary of the Standard Model. In here we can see the quarks, up-down, charm-strange, top and bottom, with their mass, charge, and spin. The leptons, there are 6 also: electron, muon, and tau, with their neutrinos: electron neutrino, muon neutrino, and tau neutrino. And the boson particles. In here we can see the weak force that is divided into the Z and the W boson, the photon, that is the unit of light, the gluon that bonds together the quarks, and the Higgs boson. In this one is another representation of the Standard Model. In the center, you can see the Higgs boson. Let's talk about it. The Higgs boson and its relationship with mass. The Higgs is the particle responsible for giving mass to other particles. But what is mass? When you think of things having mass, you usually think that it means that they have stuff, right? Well, it's not actually stuff. Particles have no mass have mass, but they don't have volume. Mass is a characteristic of a particle, like charge. Some have it and some don't. It's just a different kind of charge or property. Nicknamed the God particle, the Higgs boson was proposed in the 1960s by the British physicist Peter Higgs as a way of explaining why other particles have mass. The Higgs boson is theoretically responsible for mass, without which there would be no gravity and no universe. Scientists smash protons together to recreate conditions similar to the instant of the Big Bang, and they do it in what is called the Large Hadron Collider, or nicknamed LHC. There is one located between France and Switzerland, as we can see in the map. In here, protons are present in the nucleus of the atom and the basic unit of matter. Protons are composed of even smaller particles, the three quarks held together by massive gluons. Higgs boson in a lab. The first step is protons are accelerated at 99.99% of the speed of light. Quarks and gluons inside the protons collide and explode with enough energy to recreate the Higgs particle. The Higgs particle has 100 to 200 times the mass of a proton and will last less than a millionth of a billionth of a second before decaying into spray of other particles. Evidence of the Higgs particle will be found in the telltale spirals and streaks left in the Large Hadron Collider detectors by the particles created as it disintegrates. This is another explanation in a different view of the Higgs boson. We know that fish are born in water, and they don't feel or know that they are surrounded by it. We know that water is made of molecules, of hydrogen and oxygen bonded together. Well, in a world it's in the same way. We have mass and we live in a world and we move in this ocean of particles that is called, in other words, the Higgs field. And this Higgs field is made with Higgs particles. Thank you for watching this video.